Let us discuss behavior of the infinite series given using the help of behavior of sequence of partial sum. Whenever you have limit n tends to infinity Sn, that is limit n tends to infinity nth partial sum will give you a finite value. In that situation you will conclude that the given infinite series is also convergent. In case you will get limit n tends to infinity Sn equals infinite value. That is, when you evaluated limit n tends to infinity Sn, you obtain positive infinity or negative infinity. In that situation, you will conclude that the given infinite series is divergent. Let us look at an example. Consider the series 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus etc. plus 1 by n into n plus 1 plus etc. up to infinite terms. Here we have first term u1 equals 1 by 1 into 2, which can also be written as 1 by 1 minus 1 by 2. The second term u2 equals 1 by 2 into 3 can also be written as 1 by 2 minus 1 by 3. Similarly, third term u3 equals 1 by 3 into 4 can also be written as 1 by 3 minus 1 by 4. Therefore, the general nth term u suffix n, which equals 1 by n into n plus 1, can also be written as 1 by n minus 1 by n plus 1. When you consider Sn, which is the nth partial sum, which is sum of terms u1, u2, u3 up to un, you will have 1 by 1 minus 1 by 2 added to 1 by 2 minus 1 by 3, which gets added to 1 by 3 minus 1 by 4 plus etc. plus 1 by n minus 1 by n plus 1. Notice that negative 1 by 2 gets cancelled with positive 1 by 2. Negative 1 by 3 gets cancelled with positive 1 by 3. In the next step, we will have negative 1 by 4 getting cancelled with positive 1 by 4 and so on. Therefore, after cancelling maximum number of terms, we will be left out with Sn equals 1 minus 1 by n plus 1. Having found a simplified expression for Sn, which is the nth partial sum, now we will evaluate limit n tends to infinity on Sn. If we get a finite value, we will conclude that the given infinite series is convergent. If you get limit n tends to infinity, Sn equals positive or negative infinity, in that case, we will conclude that the given infinite series is divergent. Here, when you give limit n tends to infinity to Sn, first term is just a constant, therefore limit has no effect on it. When you give limit n tends to infinity to the second term, which is 1 by n plus 1, it becomes 0. Therefore, we have limit n tends to infinity Sn equals 1 minus 0, which equals 0 and which is clearly a finite value. Since we obtain a finite value when you computed limit n tends to infinity Sn, here for this case, for this example, we will conclude that this given infinite series is convergent and it converges to 1. Let us look at another example. Consider the series 1 square plus 2 square plus 3 square plus etc. plus n square up to infinite number of terms. For this particular infinite series, the nth partial sum will be Sn, which is the sum of u1, u2, u3 plus etc. up to un. That is, Sn equals sum of first n terms of the given infinite series. We have Sn equals 1 square plus 2 square plus 3 square plus etc. plus n square, which is sum of squares of n natural numbers, which has the basic formula n into n plus 1 into 2n plus 1 upon 6. Now let us evaluate limit n tends to infinity on nth partial sum. We have, when you give limit n tends to infinity to this expression, you will get the answer as positive infinity. Since we are obtaining limit n tends to infinity applied on nth partial sum as an infinite value, here for this particular infinite series, we will conclude that the given infinite series is divergent, which means that it does not converge to any definite value. This is an interesting observation of predicting the behavior of the infinite series after we have evaluated limit n tends to infinity on nth partial sum, which is Sn. When limit n tends to infinity Sn is giving a finite value, you are able to conclude that the given infinite series is convergent. And when limit n tends to infinity Sn is not giving a finite value, you will easily conclude that the given infinite series is also not convergent. There can be situation wherein the given infinite series neither converges nor diverges. This is the case when the given infinite series will oscillate finitely or infinitely. This oscillatory behavior of the infinite series can also be predicted using nth partial sum. If you consider the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus etc. up to infinite number of terms, for this particular infinite series, the nth partial sum will be Sn equals 1 minus 1 plus 1 minus 1 plus 1 plus etc. up to n terms. If you take n as an odd value, for example, if you take n equals 1, then you have s1 equals 1. If you take n equals 3, you have s3 equals 1 minus 1 plus 1, which is sum of first 3 terms of the infinite series, which will again give you the answer as 1. So you can generalize that whenever n is odd, you have Sn will be 1. If you take n as an even value, for example, if you consider S2, which is the sum of first 2 terms of the given infinite series, it will be 1 minus 1, which equals 0. If you consider S4, which is sum of first 4 terms of the infinite series, you will have 1 minus 1 plus 1 minus 1 will again give you 0 as the answer. You can generalize the situation that whenever n is even, you have Sn equals 0. So there are only 2 possibilities for Sn. Either it is 1 or it is 0. The answer 1 is obtained for Sn whenever n is odd, and the answer 0 is obtained for Sn whenever n is even. Therefore, we have limit n tends to infinity, Sn takes the value 1 or 0. Since we have limiting values oscillating between two finite values, we will conclude that the given infinite series shall also oscillate finitely. Suppose you have a situation wherein limit n tends to infinity Sn oscillates between negative infinity and positive infinity. In that case, you will conclude that the given infinite series oscillates infinitely.